A group of people live chained in the cave all their lives, facing a blank wall. Some objects pass in front of a fire behind them, projecting shadows on the wall. The prisoners give names to the shadows, believing that they are true objects, but they are just shadows of reality.
The new frontier of wireless communication systems is to encode information in both space and time configurations of the electromagnetic field. Like any journey to uncharted places, things aren't that simple, and it soon turned out that we can't do everything we want. There are some limitations which, at the physical layer level, are modeled in terms of spatial correlation. But what is the origin of the spatial correlation? Is it just a shadow of some fundamental feature of our universe? Let's take a look outside the cave. Above, we have the upper part of the physical layer, with a lot of bits to send. Below, we have the bottom part of the physical layer, which we'll call the deep physical layer. In this world, Maxwell's equations set the rules. We need a gateway to connect these two worlds. This gateway is the antenna. There is no other way to pass from the virtual world of bits to the physical world of the electromagnetic waves. All information must pass through this narrow gate. But what makes this gate narrow? Let us consider an electric charge in free space and an observation point. When the charge is accelerated, an electromagnetic pulse reaches the observer after a delay, fixed by the speed of light. Let us now consider a second charge. The two charges transmit an electromagnetic pulse simultaneously. However, due to the different distance, the observer will see two pulses arriving at different times. The mean value of the arrival time is the delay time of this simple communication system. This delay has no particular role in our discussion, so we will keep it constant. All the points on the red curve give the same delay. The points that have the same arrival time average difference are placed on the yellow curve. Suppose now that the two sources are subjected to a harmonic acceleration of period t. The delay causes a phase difference between the two signals at the observation point. Let's move the observation point along the red curve. The average time delay does not change, but the mean difference does. We move the observation point along the red curve until the phase difference changes by pi. We then repeat this operation, obtaining a set of points that have a special particularity. The phase difference increases by exactly pi at each point. The positions and number of these points depend on the distance of the two charges. As the distance decreases, the number of points also decreases. If we have other charges between the two charges, more harmonic spatial signals arrive at the observation point. However, the fastest phase variation is always given by interference from the most distant charges. The field along the observation curve is a superposition of spatial harmonic signals, whose fastest variation is fixed by the charges at the extremes of the radiant system. The field can be approximated by a band-limited function, whose sampling points are these special points. All this is true for any radiating system, also for the most sophisticated massive MIMO antennas. But what is the connection with spacetime communication systems? Let's consider a simple example. We want to transmit a sequence of bits, using spacetime coding with binary phase shift keying. We associate a piece of information to each sampling points. The receiving antennas are placed in the positions of the sampling points. Measuring the field value allows to retrieve the string of bits. This is repeated in time, allowing to encode information in space and time. Now, we can unlock the secret behind the spatial coding of information. There are only some points in the space, wherein we are free to fix the value of the field. The field and the remaining points are just linear combinations of these values. This limits the amount of information that we can encode in the space domain. The yellow curves are a graphical representation of the information flows in the space around the antenna. If the receiving antennas are placed along the same curve, we can receive only one stream of bits. But when they are placed along different curves, we can receive multiple streams of bits. What we observe at the upper level of the physical layer is the shadow of how this basic limitation acts at the deep physical layer level. All of this can be made rigorous using mathematics. But mathematics keeps the role played by one of the most important features of our universe, the finite speed of light in the dark.
And now we can finally get out of the cave and observe the field that runs through the space, drawing information flows.